Hello, this is the section 8.1 and 8.2 lesson on the topics of factors, multiples, even, and odd. Chapter 8 deals with the general topic of number theory. And here's a definition of number theory that I stole off the internet. Number theory is the branch of mathematics that deals with the properties and relationships of numbers, especially the positive integers. And so this is going to be a little change of gears for us. We're not going to be dealing so much with arithmetic and explaining why arithmetic works. In this chapter, we're going to look at positive integers, or also called counting numbers, and look at properties of those positive integers and relationships between them. So we're not going to be dealing with decimals or fractions, and we're not going to be doing a lot of arithmetic. We will, however, be using properties of arithmetic that we've learned earlier on in the semester. So number theory involves a lot of definitions, and so we need to start off with three definitions that are actually much easier to state by example than in words. But let's give these definitions in words, and we'll follow up each definition with an example. So first is the definition of divisibility. So a number A is divisible by a number B, or stated in other terms, B divides A, if A divided by B is a whole number. So a lot of letters there, hard to understand. Let's illustrate it with an example. So the number 8 is divisible by 4, since 8 divided by 4 equals 2. And that's all we need to do to show divisibility. Just divide one by the other. If we get a whole number, they're divisible. Second definition, B is a factor, or we also say that is a divisor of a number A if there is a whole number C such that A equals C times B. Again, kind of confusing definition because there's lots of letters, so let's illustrate it with an example. 6 is a factor of the number 18, since 18 is equal to the whole number 3 times 6. And so that's all we need to do to show that 6 is a factor of 18. Just show that 6 times something equals 18. Now, there are other factors of 18. Right here from this one equation, we see that 3 times some whole number equals 18. So that means that 3 is also a factor of 18. And then we could come up with some other factors like 2 and 9. Those are factors because 2 times 9 equals 18. We could list 1 as a factor, and 18 as a factor because 1 times 18 is 18. So there are lots of different factors of 18. Our third definition, A is a multiple of B if there is a whole number C such that A equals C times B. So let's do an example. 24 is a multiple of 12 since 24 equals the whole number 2 times 12. So there is one multiple of 12. Another multiple of 12 would be like 36 because 36 is 3 times 12. 48 is a multiple since 48 equals 4 times 12. So there are lots of different multiples. Now, one important thing to remember about these ideas is that they apply only to whole numbers. They don't apply to decimals or fractions, only whole numbers. And in fact, all the ideas that we talk about in this chapter are really going to apply to only whole numbers. Now, let's state a couple of other definitions, and these are definitions that I'm sure you're already familiar with. The first is the definition of an even number. Now, there are lots of different ways to define an even number. I'm going to state one way here, and then we'll state an alternate way. And the book includes some other alternate definitions of even. But here's where we're going to start. A counting number is even if it is divisible by 2. So an example, 36 is even since 36 divided by 2 equals the whole number 18. And so there we just showed that 36 fits our definition of even numbers. Now, another way that we may have determined that 36 is even is to just look at the ones digit, see a 6, and say 6 is even, therefore 36 is even. And that is another way of determining whether a number is even or not. But this is the definition that we're going to start with. Now, let's look at this equation right here and rewrite it as an equivalent multiplication equation, which says that 36 is equal to 2 times 18. So this equation says that 36 is equal to 2 times some whole number. And so that observation is going to lead us to an equivalent definition, which says that a counting number is even if it equals 2 times another counting number. And this is actually the definition that we're going to use in our examples and in our activities. A counting number is even if it equals 2 times another counting number. Now let's talk about odd numbers. And again, we'll start off with one definition and then we'll get a couple of other equivalent definitions. So a counting number is odd if it's not even, or stated another way, it's odd if it's not divisible by 2. So as an example, 15 is odd since 15 divided by 2 equals the decimal 7.5. Or if we wanted to write it in terms of remainders, we would say it's 7 remainder 1. So either way I look at these answers, I see that I don't get a whole number. 15 is not evenly divisible by 2, and so therefore 15 is odd. Now another way I could determine that 15 is odd is by looking at the ones digit and say, well, 5 is odd, therefore 15 is odd, and that is valid. In next section we'll see a little bit about why that method works, but right now we're just illustrating what this definition means. Now let's take this equation here and rewrite it in slightly different form. I could say that 15 is equal to 2 times 7 plus 1. So what we've shown here is that my odd number is equal to 2 times some whole number plus 1. So that leads to our next equivalent definition, that a counting number is odd if it equals 2 times another counting number plus 1. And this is the definition of odd that we're going to use in this lesson and in the homework. Now, one thing we like to do in number theory is to state and prove theorems. So here is an example of a theorem in number theory. It says that the sum of two even numbers is true. It is even. And so that means that if I add two even numbers, I'm claiming that I'm always going to get an even number. Now, a theorem is a mathematical statement proven to be true in every situation. And so we can prove that no matter what two even numbers I choose, no matter how big or small they are, I'm always going to get an even number. Now here in this lesson we're not going to formally prove this statement, but we will kind of illustrate why it's true. So let's illustrate why this theorem is true with the numbers 16 and 12. So 16 and 12 are both even numbers. We are going to add them together and show that we get an even number. And our explanation is going to help illustrate why this is true. And so when we do this, we're going to use two things. First, definitions, specifically the definition of even numbers. And then second, we're going to use properties of arithmetic, and specifically the distributive property. We could use other properties like a commutative property or associative property, but we're going to use mostly the distributive property here. Now, in our explanation, we will not use arithmetic, meaning we're not going to just add these two numbers and be done with it. Throughout the semester, whenever we've explained why we do things the way we do, we've never just done the arithmetic and be done with it. We've always tried to use definitions or meanings along with other properties that we already know. And so this goes back to an idea that we saw back in chapter 1, the difference between how and why. And so I've got a problem here which involves just arithmetic, namely adding 12 and 16. If I stay within that problem, then all I'm doing is explaining how to solve the problem. And that's not what I want to do. I'm not interested in the how, I'm interested in why. So to explain why, I need to look outside the problem and use some big mathematical ideas. Those big mathematical ideas are definitions and properties. So I'm going to use those definitions and properties, apply them to my problem, and that's going to help explain why my theorem is true. So as I mentioned earlier, the key idea or the property that we're going to use here in our explanation is the distributive property. So let's review that briefly. The distributive property looks like this. Say I've got a number a times the sum of two numbers b plus c. Now these numbers could be whole numbers, they could be negatives, they could be decimals, they could be fractions, doesn't really matter. Here we're going to work with just whole numbers. So a times the quantity b plus c. Distributive property says that I can distribute that a across to get a times b plus a times c. Now I can also go backwards, meaning if I have an expression like this, I could factor the a out and write it as a times b plus c. So it works either way. In this example, we're actually going to work backwards. We're going to start with something that looks like this and write it in something that looks like that. So let's get back to our example. So here's our theorem. The sum of two even numbers is even, and we want to illustrate why this theorem is true with the numbers 16 and 12. So we're going to start off by writing down 16 plus 12. Now we're not going to just do the arithmetic and add those two numbers to get 28 and say 28 is even and we're done. Again, we're not going to do the arithmetic. We're going to use definitions and properties. So first I think, well, 16 and 12 are even. What does that mean? Well, by the definition of even numbers, that means that I can write 16 as 2 times some number, which happens to be 8, and 12 as 2 times some number, which happens to be 6. So there I've used my definition of even to rewrite these two numbers in different forms. So now I look at this right-hand side, and I say, well, wait a minute, that looks like the right-hand side of my distributive property. Both of these terms here have a factor of 2, so I can factor that 2 out and write it as 2 times 8 plus 6. So there I'm using the distributive property. So now I say to myself, well, wait a minute, 8 plus 6, well, this is a whole number, and that's a whole number. If I add two whole numbers together, I get another whole number, or more specifically, a counting number. So I have 2 times a counting number. Now that counting number happens to be 14, but we're not interested in the exact value of that counting number. It's just a counting number, and that's all that's really important. And so now I say to myself, well, what I have here is this sum equals 2 times a counting number. Well, that's just exactly the definition of even. So therefore, 6 plus 12 is even by definition. So there we go. That's these calculations help illustrate why our theorem is true. We didn't do any arithmetic. We just used definitions and properties of arithmetic. Now, you may ask yourself, why did we go to all this work? Wouldn't it have been easier just to add 16 and 12 and say we get 28 and be done with it? Well, yes, it would have been easier, but that wouldn't have given us any insight into why that sum is even. All that would have done is shown us that in this particular case, with these particular numbers, we get the particular even number 28. But what we've really done here is outline a general strategy that'll work for any set of numbers. There's absolutely nothing special about the numbers 8 and 6. Here, all that's really important is that they're counting numbers. And so we could apply this idea to other numbers. So as an example, let's do the same problem, illustrate why this theorem is true with the numbers 154 and 218. So I'm going to follow the exact same argument. 154 plus 218, those are both even, so I can write the first one as 2 times 74 plus 2 times 108. Again, by the definition of even. And then I can factor out the 2 to get this by the distributive property. So I have 2 times a counting number plus a counting number. And so we've got 2 times a counting number. And so therefore, 154 plus 218 is even by definition. Notice that's the exact same argument, exact same work. We just have different numbers. But the exact values of the numbers are irrelevant. All that's important is that they're counting numbers. So this argument that we set up can be applied to any even numbers, not just the specific even numbers 12 and 16 or 154 and 218. So that's it for this lesson. Your assignment is to read sections 8.1 and 8.2.